Hi all. So today we are going to start module 5. Sorry. So module 5 has two parts, the radar antenna and the radar receiver. So today we'll start on what is radar antenna, the functions of radar antenna, and antenna parameters I'll be dealing in the next video. So today we'll do functions of radar antenna, which is a small topic, and then I'll quickly start with what are reflector antennas. Okay. So let us see what are the functions of radar antenna. So as we all know, a radar antenna is a very important part of any radar, right? So usually this antenna is a device that acts as a transducer. So it provides a good match between the feeding line and a local source of power and free space. So it is a transducer between the propagation in space and guided wave propagation in the transmission lines. Okay, so usually we need a good matching between the antenna and the feeding line. Okay, so without good matching, as we all know what is matching, right? So we have learned about it in the previous semester. So without a good match, we will not have a good radiation. Okay, now this antenna concentrates the radiated energy in the direction of the target. So it is supposed to concentrate the radiated energy in the direction of the target, right? So this is measured by the parameter called as antenna gain. Yeah. So as I said, if the antenna is not properly matched to the free space, why should it be matched to free space? Because antenna is supposed to radiate into the free space. So there should be proper matching between the antenna and the free space. So if it is not if that is not the case, then the power would be reflected back towards the transmitter. Transmitter in the sense the radar itself, because in the radar, transmitter and receiving are combined, right? Because we have a duplexer. So if proper matching is not done, there would be reflection, as we all know, right? And then this would result in a loss in the radiated power. So if proper matching is not done, we know that there would be reflections, right? Yeah. So matching is required between the antenna and the free space. Now, so what are the other essential functions? So it has to transfer the transmitter energy into the signals in space, and it should energy should also be also have the required efficiency and the distribution, in the sense there is a required radiation pattern that has to be provided by the antenna, right? That means what should be the beam width, what should be the directivity, and so on. So that all should be satisfied with the proper required efficiency, which is to be supplied by the radar antenna. So it ensures that the signal has the required pattern, that is a radiation pattern, right? So required pattern in azimuth as well as elevation, that is theta and phi, and then what is the directivity? Is it narrow beam width or broad beam width? So according to the application, it should ensure that the radiation pattern is proper. So this, yeah, so there are certain applications where azimuth beam width should be narrow, right? So in such cases, accordingly, the radar antenna should provide the pattern, okay? So asymmetrical beam width, asymmetrical beam shape will be discussed in the coming topics, okay? It is called as fan beam usually. Now the echo energy which is collected should be by the antenna and scattered back to the radar from the target. So usually the echo signal which is coming from the target should be collected by this antenna. So this is actually measured by the effective aperture, right? Yeah. Now another thing is it should provide the required frequency of target position updates. Frequency in the sense there should be a specific time limit, right? Where the target position update should happen. So every sweep, so in every sweep, the target position updates will happen usually. So that is dependent on what is your PRF, that is pulse repetition frequency, right? So that all should be maintained by the antenna. So usually if the antenna is mechanically scanned, it is mechanical in the sense by some operator or some device at the receiving section. So in that such case, this is associated to the revolution rate. So some antennas revolve, right? For example, conical scanning antenna, they have a particular revolution, right? So there should be a rate of revolution to be maintained, and that should be done by the radar antenna. So usually we can't accommodate very high revolution rate because that will have a mechanical problem, right? It is going to be very complicated if the revolution rate is high at the receiving section or the radar antenna point, right? So this high revolution rate can be a significant mechanical problem, given that the radar antenna in certain frequency bands can have a reflector with immense dimensions and can have and can weigh several tons. So these are the constraints, because some antennas are very huge, right? And can weigh several tons. In such cases, it is very difficult to mechanically rotate the antenna getting a very high revolution rate. So that is what is meant by this. So it must measure the pointing direction with a high degree of accuracy. So that means the directivity, the required directivity should be maintained so that it points exactly to the desired target direction. So as I said earlier, it should concentrate the radiated energy to the desired target direction. And it should also collect this echo energy which is scattered back to the radar coming from the target. So this previous topic, that is concentrating the radiated energy in the direction of the target, is measured by antenna gain, correct? So gain will tell you if it is actually doing this job, right? Similarly, collecting the echo energy scattered back to the radar from the target. This also is a measure of antenna effective aperture, that is AE, capital A suffix E. So AE, as AE becomes higher, this collected energy becomes greater, right? AE is the effective aperture of the antenna. So if that area is higher, we get more energy which is collected by the radar antenna, right? Now, next is, so it measures the angle of arrival of the received echo signal so as to provide the location of the target in azimuth as well as elevation. So that location of the target has to be decided by this radar antenna based on what is the angle of arrival of the received echo signal. So location in the sense elevation and azimuth. Another important point is radar antenna acts as a spatial filter. What is spatial filter? Because the main job of the antenna is to separate the targets, that is the desired targets, in the spatial domain, correct? Because we are talking about the targets which are in free space. So in the spatial domain, it has to separate the desired targets and then reject all the undesired signals coming from different directions other than which are there in the main beam of the radiation pattern. So that's why it acts as a spatial filter. Next is, it should provide the desired volumetric coverage of the radar, right? So the beam should be in such a way that it is actually covering your desired target. It shouldn't be too narrow that it doesn't cover the target. It shouldn't be too broad that it covers the undesired signals also. So it should provide the exact coverage. And then it usually establishes the time between the radar observations of the target, that is revisit time, okay? So the frequency, so that is what is the same as the previous topic, that is frequency of the target signals, right? That is PRF or the sweeps. In every sweep, we'll take one observation, right? So that time would be established by the radar antenna. So in addition to all of this, we know that the antenna is a very important part of the radar system. And usually when you see a radar, the first thing which you would see is the antenna's picture, right? So this antennas in radar are usually what we require is it should be big, it should be huge. Okay, so but there should be limits of mechanical and electrical tolerances. Okay, so larger the antenna, better would be the radar performance, because larger area would assure that the echo energy which is captured back at the radar is more. Okay, so but the transmitter could be smaller. So, but and the total power which is sent by the transmitter should be proper, though the transmitter is small. Okay. Now we all know that there is an equation J is equal to 4 pi AE by lambda square. So in that equation, we know that the transmitter antenna gain, that is G, and the receiving effective aperture, that is AE, are directly proportional. So as you increase the antenna gain, effective aperture, your gain is going to increase, right? So that's why we say that we need a larger area of the antenna. G is equal to 4 pi AE by lambda square, right? That we have studied since last year, right? So another important thing is most of the radar antennas are directive. So we don't have isotropic, real-time isotropic antennas, right? So we want most of the radar antennas to be directive, and there should be some means in the current modern situations. We need means for steering the beam. Okay, so beam steering is what we'll be learning in phased array antennas. So phased array antennas are those which employ beam steering. So you can steer the beam as per the directions of the desired targets. So directive antennas means you have narrow beam widths, and then that would result in accurate angular measurements. That means it will exactly point the direction of the target. Okay. So another important advantage of all these is we usually operate these radar antennas in microwave frequencies. So using these microwave frequencies for radar has an advantage that the directive antennas with narrow beam widths can be achieved with smaller physical size, that is aperture of smaller physical size. So that is the importance of operating in microwave frequencies. Otherwise, if you don't use microwave frequencies, the size, physical size would keep increasing, correct? So all these are operated usually in microwave frequencies. So there are different types of directive antennas. So we would be learning about the reflector antennas and the various feeds which are used in reflector antennas, phased array antennas. So these two are what we'll be learning in this module. Okay. So let us quickly go to the reflector antennas. Okay. So yeah. So this is what we have in reflector antennas. So what you see in this figure is a parabolic surface. So this parabola, which you see here, it works well as a reflector of electromagnetic energy. Okay, so this is very popularly used. You can see it in your homes, that parabolic dish antenna. Okay, now this parabolic surface here, which you see the larger part, this has a dimension D. So this is usually the diameter because we don't have the other part, right? So this dimension, this is called as the diameter, or you can say the dimension D. So this parabolic surface is illuminated by a source. Okay, so this source is called as feed. Okay, the antenna feed. And this feed is placed at the focus of the parabola. So this point is the focus of the parabola. Okay, where you keep the antenna feed. So this parabolic surface is illuminated by the feed which is kept at the focus of the parabola. Okay. This parabola converts the spherical waves which are radiated from this feed to a plane wave like this, which you can see it in the plane wavefront. Okay. So this is because any ray which is radiated from this focus that intersects this parabolic surface, it is reflected in the direction which is parallel to the axis of the parabola. So this is the axis of the parabola. So the radiated energy which is hitting this parabolic surface is reflected parallel to the axis of this parabola. Okay. Another thing is the distance which is traveled by any ray which is coming from this feed. Okay, so this distance, like from this to this and then this to this. Similarly, this distance, this and this. So all these distances which are traveled by any ray from this focus or the feed and then reflected to the plane perpendicular to the parabolic axis. This, okay, it is all the same. Okay, so no matter at what angle they are coming out of the feed. Okay, so whichever angle they are coming out, they are going to be. Okay, so this is the parabolic axis. So this is the line which is plane which is perpendicular to the parabolic axis. Okay, so the distance traveled by any ray which is coming from this feed, okay, and then reflected from this parabolic surface to a plane perpendicular to the parabolic axis, to this wavefront. Okay, so this distance is going to be same for any ray which is emanated from, at any angle from the feed. Okay, that are the different characteristics of this parabolic antenna. So this parabolic antenna, this is called as paraboloid. Okay, so there are several ways in which this paraboloid can be used as antennas. Okay, um, so this, yeah, so this whatever you see here is a circular parabola. Okay, or another name is paraboloid, as I said. So this is illuminated by the antenna feed. So there is another figure. So this, yeah, same thing. Okay. So this is the paraboloid axis. So this is paraboloid, which is circular parabola. Okay. So when it is properly illuminated by the source, that is feed, which is kept at the focal point focus, this paraboloid generates a very symmetrical pencil beam antenna pattern, because the rays which are coming out towards this wavefront, right? These are plane waves, and they have very high intensity. So they generate a very symmetrical pencil beam antenna pattern. And hence, this antenna is very popular antenna used for tracking radars. So the name which you would be aware of is dish. So sometimes this paraboloid reflector is called as dish antenna. Okay, so that is, yeah. So this is how the feed would be placed, and this is the vertex. This axis is the paraboloid axis. Okay, so the place of focal point is the place where you keep the feed. Clear? So next, yeah, this GIF will give you a clear picture of how this parabolic reflector is used as a receiver. So obviously we are going to use this antenna as receiver as well as transmitter, right? So if it is acting as a receiver, the incoming signals from the target are coming and hitting the, so the same thing which happens in this direction from the feed to this wavefront, right? The same thing happens in the receiving part also. So the incoming signals which are coming and hitting the reflecting surface is going and hitting back the feed, reflecting from here and hitting back the feed, and then this would be connected to the receiver section, correct? So the back of the feed will be the place where you receive the signals, right? You see this? So energy is hitting the reflecting surface, and then it is going back to the feed. So this is the axis of the parabola, yes, and then this feed, the back of this feed can be used as the receiving section. Clear? Yeah. So this is how the parabola works. Paraboloid works. Okay. The next is section of a paraboloid. Okay. Yeah. So section of a paraboloid. So instead of having a circular shape, so the previous slide what we saw was a circular parabola. So instead of having a circular shape, consider this reflected antenna which has a elliptical shape. Okay, so this is an elliptical section which is cut out from a symmetrical paraboloid. So such a antenna, it produces an asymmetrical beam shape which is called as fan beam. Okay, so it is called as fan beam. Okay, fan beam. Okay, so fan beam is nothing but asymmetrical beam shape. That is, sometimes we need broader beam width in one way, that is maybe azimuth or elevation, and narrow in the other orthogonal plane. So such an asymmetrical beam shape is called as fan beam. So in order to get fan beam, suppose your application requires fan beam, then you what you would prefer is a elliptical shape paraboloid. Okay. So this is often used for two-dimensional air surveillance radars. So what you see here is such a radar where you can see this is an elliptical shaped, okay, so parabolic surface, okay. So it has a different curvature in horizontal and vertical planes, okay. So the different curvature makes sure that the beams are different in the two planes, that is the elevation and azimuth. So sometimes in air surveillance radar, we need azimuth beam width to be narrower than the elevation beam width. So vertical beam, and the vertical beam is shaped to provide a broader coverage. The horizontal beam, that is azimuth beam, is made to cover a narrow beam width. Okay, so for such applications we need this elliptical parabolic surface. Okay, so these are other pictures which shows the elliptical surface. So here you can see the elliptical surface, and this point which you see here in the previous slide also it is there, this thing. So this is actually the field. Okay, so it is placed at the focus. Okay, but then this is the support of the antenna. So this feed can't be left in the air, right? So there should be some support. So all these are waveguides, and what you see here is horn antenna, which is used as the feed point. So this provides the feed, and it also acts as a receiving point. Okay, and then this is connected to the receiving section. Okay, so these are the waveguides which you can see here. So these are the supports. Okay, support of the feed. Okay, so these are the other pictures of the same section of the paraboloid. Clear? Yeah, so this is how a pencil beam will look like. So it is same. So you can see a circle here. So the azimuth as well as elevation both are same. Okay, so the beam width for both elevation in the plane of elevation, azimuth as well as elevation is the same. So this is a pencil beam. Now what is fan beam? See this. So this is asymmetrical. You can see azimuth is narrow and the elevation is broad. So, and the antenna is like this. See, so this is elliptical shape. This is a circular paraboloid. This is elliptical shape because you need an asymmetrical beam shape, that is fan. Okay, so that's the difference between pencil beam and a fan. Clear? So that's all for today. So what is, we just saw what are the functions of antenna, what is a reflector antenna, what is a paraboloid, and what is a section of a paraboloid which generates a fan beam. In the next video, we'll see the different types of feeds which can be used for the paraboloids. Okay, thank you.